Having already introduced the definition of congruence modulo n, now we're going to introduce some properties of congruence modulo n. First up, let's talk about multiplication. Now, the definition of A being equivalent to B modulo n was about n being a factor of something. It's about factoring. So it's actually pretty easy to make statements about multiplication. So here's the theorem we'll prove. If I have one equivalence mod n, A is equivalent to B, and another equivalence mod n, C is equivalent to D, then I can multiply them together to get AC is equivalent to BD modulo n. Notice that all three statements are modulo n. Well, if A is equivalent to B modulo n, then A must be a multiple of n plus B, and if C is equivalent to D modulo n, then C must be a multiple of n plus D. And I just multiply those together. A times C is going to be the first term times the second. Now, once you expand everything out, lots of terms have an n that can be factored out. This times this has an n factorable. This times this has an n factorable. This times this has an n factorable. The only thing that might not is b times d. So I factor an n out of all the other terms, and then I have bd here. But if I subtract bd from both sides now, I'll have ac minus bd is equal to n times this giant parenthetical term. In other words, n is a factor of AC minus BD, and that's exactly the definition that A times C is equivalent to B times D modulo n. So if I have two equivalences modulo the same n, I can multiply them together and get a third new equivalence modulo the same n. As a corollary, if A is equivalent to B modulo n, I can multiply both sides by the same number k. Well, k is certainly equivalent to itself modulo n. Remember, we are talking about an equivalence relation, and therefore it's reflexive. Every number is equivalent to itself. So if I simply take the theorem above and say A is equivalent to B and k is equivalent to k, modulo the same n, so I multiply A times k is equivalent to B times k, and that's exactly what we have here. Also, I can multiply a given equivalence against itself. If A is equivalent to B modulo n, I can multiply it by A is equivalent to B modulo n to get A squared is equivalent to B squared modulo n. I could do that over and over again to get any positive power. A to the k is equivalent to the same positive power B to the k modulo n, from the initial assumption that A is equivalent to B mod n. However, it was quite important we had positive exponents there. Negative exponents are going to be a trickier thing to work with because we have to understand what we mean by negative exponents to begin with. If I write, for example, 5 to the negative 1 power, you might think that represents 1 over 5, and that would not be an integer, and therefore we can't even talk about modular equivalence. The definition, remember, required all the terms to be integers. So negative exponents can be redefined to mean something else, but we'll have to address that later. Well, if we can do multiplication of modular equivalences, can we also do addition? Yes, we can. If A is equivalent to B modulo n, and C is equivalent to D modulo n, then I can add them together. A plus C is equivalent to B plus D. Well, first, let's assume n is a factor of A minus B. In other words, A is equivalent to B mod n. And similarly, since C is equivalent to D mod n, we get n as a factor of C minus D. Of course, if n is a factor of two different numbers, those parenthetical terms, then it's a factor of the sum, A minus B plus C minus D. In other words, n is a factor of A plus C minus B plus D, simply rearrange terms. And that's exactly the definition that A plus C is equivalent to B plus D. Therefore, if you have two different modular equivalences modulo the same n, you can add them together, no problem. And we have similar corollaries to the last slide. I can add the same constant to both sides. K is equivalent to itself, so just like last time we then multiplied these two, well, now I can add them, and I get A plus K is equivalent to B plus K. So assuming A was equivalent to B to begin with, you can add the same number to both sides and they remain equivalent. Do be careful, however. The base of modular equivalence n was the same in every statement on the previous slides. If you have equivalences modulo different bases, then you have a trickier situation. So if you are changing base from one equivalence to another, the same results might not hold. Really common mistakes are things like this. If A is equivalent to B mod n and C is equivalent to D mod m, then I just add them up. A plus C is equivalent to B plus D modulo n plus m. I see this every single semester I teach this course. But that's just not true. It's not how it works. For example, 1 is equivalent to 3 mod 2 and 1 is equivalent to 1 mod 6. Those are both true statements. But if I attempt to do that same thing, 2 is not equivalent to 4 mod 8. That's false. So just adding everything up, including the bases, does not necessarily yield a true statement. The naive result for multiplication also doesn't hold. 1 is equivalent to 3 mod 2, and 3 is equivalent to 3 mod 5, but if I tried to multiply them together, including the bases, 3 is not equivalent to 9 mod 10. So it's important in the theorems we had before that the base of modular equivalence does not change from one line to the next. So when you do have multiple modular equivalences of different base, you do have to be careful. So we've talked about multiplication of modular equivalences, and we've talked about addition of modular equivalences. I would remark that means we can do subtraction. If you multiply by -1 and then add, that's the same thing as subtracting. But what about cancellation? Cancellation, unfortunately, is trickier. If a times k is equivalent to b times k mod n, you might not be able to simply cancel the k from both sides and immediately conclude a is equivalent to b mod n. For example, 6 is equivalent to 2 mod 4 because 4 is indeed a factor of 6 minus 2. So 2 times 3 is equivalent to 2 times 1 mod 4. But you can't just cancel out the 2's because 3 is not equivalent to 1 mod 4. 4 is not a factor of 3 minus 1. So cancellation isn't as immediate as you might hope, but there is something we can say about cancellation. If a times k is equivalent to b times k modulo n, then a is equivalent to b modulo a different base, n over the GCD of k and n. So if you want to cancel a shared factor k from a modular equivalence, you can do so. However, in stark contrast to all the theorems from the previous slides, you have to change the base of the modular equivalence by dividing out by the GCD of the original base and the number you just canceled from both sides. Let's prove it. I'm going to call that GCD, I'm going to call it D. So since D is the greatest common factor of k and n, it's a factor of both of them. So k can be written as d times something, x, and n can be written as d times something, y. And furthermore, those bits that are left behind, the x and the y, must be relatively prime from one another. Also, we get to assume ak is equivalent to bk mod n. In other words, n is a factor of ak minus bk, which means ak minus bk can be written as a multiple of n. However, k can be replaced with dx, and n can be replaced with dy, so I get a dx minus b dy is equal to dyj. This is not a modular equivalence note, this is simply an equality of integers, so I can cancel the d from both sides. Ax minus bx is equal to yj. So therefore, x can be factored out of the left. Ax minus bx, it's pretty obvious how to do so. Since that's the same number as the one on the right, x must be a factor of y times j. But x was relatively prime to y, so if x is a factor of y times j and it's relatively prime to y, it must be a factor of j. So j can be written as x times something. So if I replace j with x times z, then everything here has a common factor of x, and since again I'm only talking about an equality of integers, I can cancel that x from every term, leaving a minus b as y times z. We've replaced j with x times z and then canceled the x from every term. So a minus b is exactly the same number as y times z. Y is definitely a factor of y times z, and therefore y is a factor of a minus b. Well, if y is a factor of a minus b, by definition that means a is equivalent to b modulo y. And what was y? Y is exactly n over d, n over the greatest common factor of k and n. So a is equivalent to b modulo this number right here, and that's exactly what we were trying to prove. So can you cancel something from a modular equivalence? Yes, but you also have to change the base of the modular equivalence by dividing out by the greatest common factor of your original base and the number you just canceled. However, if the base n and the number you wish to cancel k are relatively prime, then you're simply dividing out by a 1, which doesn't change anything. So this corollary, if a times k is equivalent to b times k modulo n, and k, the number you wish to cancel, is relatively prime to the base n, in other words, the greatest common factor of k and n is equal to 1, then you cancel it out and you divide the base by this common factor, but this greatest common factor is just 1, so you don't have to change it. So when the number you wish to cancel is relatively prime to your base, then things work quite nicely. Look back at the original example at the top. 6 is equivalent to 2 modulo 4. We wanted to cancel out a shared factor of 2. That shared factor of 2 is not relatively prime to the base 4, so that's why this did not work. However, we could say that 3 is equivalent to 1 modulo 4 over the GCD. That GCD was 2. So 3 is equivalent to 1 modulo 4 over 2. That is true. Okay. So be careful with cancellation. The nicest scenario is when the thing you wish to cancel is relatively prime to the base. Then cancellation works exactly as you would hope. But in general, you may have to change the base of your modular equivalence.